17.5 Wells and artesian systems. Discuss water wells and their relationship to the water table. Sketch and label a simple artesian system. According to the National Groundwater Association, there are more than 16 million water wells for all purposes in the United States. Private household wells constitute the largest share, more than 13 million. About 500,000 new residential wells are drilled each year. Wells. The most common method for removing groundwater is to use a well, a hole bored into the zone of saturation, figure 17.14. Wells serve as small reservoirs into which groundwater migrates and from which it can be pumped to the surface. The use of wells dates back many centuries and continues to be an important method of obtaining water today. Groundwater is the principal source of drinking water for about 50% of the U.S. population and provides about 96% of the water used for rural domestic supplies. Figure 17.14 Wells. Wells are the most common means by which people obtain groundwater. Top photo by Shutterstock, bottom photo by ASP/YPP/Age photo stock. The water table level may fluctuate considerably during the course of a year, dropping during dry periods and rising following wet periods. Therefore, to ensure a continuous supply of water, a well must penetrate below the water table. Whenever substantial water is withdrawn from a well, the water table around the well may be lowered. This effect, termed drawdown, decreases with increasing distance from the well. The result is a depression in the water table, roughly conical in shape, known as a cone of depression, figure 17.15. Because the cone of depression increases the hydraulic gradient near the well, groundwater will flow more rapidly toward the opening. For most small domestic wells, the cone of depression is negligible. However, when wells are heavily pumped for irrigation or for industrial purposes, the withdrawal of water can be great enough to create a very wide and steep cone of depression. This may substantially lower the water table in an area and cause nearby shallow wells to become dry. Figure 17.15 illustrates this situation. Smart figure 17.15 Cone of depression. For most small domestic wells, the cone of depression is negligible. When wells are heavily pumped, the cone of depression can be large and may lower the water table such that nearby shallower wells may be left dry.
Groundwater cone of depression. The depth of a water table is frequently changed when groundwater is pumped from a well. Groundwater flows toward a well, so over time the level of the water table tends to slope down toward the bottom of the well shaft. Notice that as the two wells pump groundwater, the level of the water table falls until it resembles a downward-pointing cone around each well. This is known as a cone of depression. A cone of depression will grow larger until the rate of groundwater recharge matches the rate of groundwater pumping. Notice that the cone of depression in the water table around the more heavily used well grows larger than the cone around the less heavily used well. The cone of depression around the heavily used well eventually grows so large that the water table drops below the level of the shallower well, which then goes dry.
Digging a successful well is a familiar challenge for people in areas where groundwater is the primary source of supply. One well may be successful at a depth of 10 meters, 33 feet, whereas a neighbor may have to go twice as deep to find an adequate supply. Still others may be forced to go deeper or try a different site altogether. When subsurface materials are heterogeneous, the amount of water that a well can provide may vary a great deal over short distances. For example, when two nearby wells are drilled to the same level and only one is successful, it may be because there is a perched water table beneath one of them. As figure 17.16 illustrates, a perched water table forms where an aquitard is situated above the main water table. Massive igneous and metamorphic rocks provide a second example. These crystalline rocks are usually not very permeable, except where they are cut by many intersecting joints and fractures. Therefore, when a well drilled into such rock does not intersect an adequate network of fractures, it is likely to be unproductive. Figure 17.16 Perched water table. Artesian systems. In most wells, water cannot rise without the use of pumps. If water is first encountered at a depth of 30 meters, 100 feet, it remains at that level, fluctuating perhaps 1 or 2 meters, 3 to 6 feet, with seasonal wet and dry periods. However, in some wells, water rises, sometimes overflowing at the surface. Such wells are abundant in the Artois region of northern France, and so we call these self-rising wells artesian. The term artesian is applied to any situation in which groundwater under pressure rises above the level of the aquifer. For an artesian system to exist, two conditions usually are met. Figure 17.17, 1. Water is confined to an aquifer that is inclined so that one end can receive water, and 2. Aquitards, both above and below the aquifer, must be present to prevent the water from escaping. Such an aquifer is called a confined aquifer. When such a layer is tapped, the pressure created by the weight of the water above will force the water to rise. If there were no friction, the water in the well would rise to the level of the water at the top of the aquifer. However, friction reduces the height of the pressure surface. The greater the distance from the recharge area, where water enters the inclined aquifer, the greater the friction and the less the rise of water. Smart Figure 17.17 Artesian Systems. These groundwater systems occur where an inclined aquifer is surrounded by impermeable beds, aquitards. Such aquifers are called confined aquifers. The photo shows a flowing artesian well. Photo by James E. Patterson. Tutorial. Artesian Systems.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe what an artesian system is and distinguish between flowing and non-flowing artesian wells. This is an example of a flowing artesian well. Basically, all you have to do is drill a hole in the ground, and then coming up out of that hole, boom, is water. It kind of reminds me of the opening sequence of the Beverly Hillbillies, where Jed's out hunting rabbits, and he shoots his rifle, and the bullet pierces an aquitard, and that aquifer underneath holds not water but oil, and it starts oozing out onto the ground. It's the same thing here, except groundwater is what's flowing out of this hole. So let's take a look at two examples of these artesian wells. We're going to take a look at one that's very close to the recharge area, and then we're going to take another look at a second one that's further away from the recharge area. So let's go ahead and take a look at the first one here. We're going to zoom in on this area. You can see here that we've got an aquifer that's confined by two aquitards, one above and one below. You can see that the top of the groundwater there is the water table. And if you extend that water table off to the right, imaginarily through the aquitard that overlies the aquifer, that is what we call a pressure surface. And if you were to drill a well down and pierce that aquitard, the water would flow up in that well to that pressure surface. So the pressure surface is above the top of the aquifer, but the pressure surface is below the ground. So as a result, this is a non-flowing artesian well. Contrast that with this situation. This is more like the example that we looked at to start with. Further away from the recharge area and at a lower elevation, the pressure surface is actually above the surface of the earth. As a result, the water in the confined aquifer wants to flow up through that well to reach that pressure surface, but basically it's hitting